Hi guys, today I am going to talk to you about empirical formula and molecular formula. You will need your notes, of course, a highlighter, a pen or pencil, calculator, as well as your periodic table. Okay, well then let's get started. So first of all, let's talk about what an empirical formula is. An empirical formula is highlight empirical formula. It is the simplest whole number ratio of elements in a chemical formula. Okay, so here is an example of an empirical formula. If I have benzene, which is C6H6. Now, benzene is a molecule, but notice that it can be reduced down to another formula. So you can actually reduce the 6 down to CH. This right here, CH, would be the empirical formula for benzene. Okay? Another one would be H2O. Now, H2O is also the empirical formula because it cannot be reduced further down. So H2O would be the empirical formula as well as the real formula of the structure, which I'll talk about in a few minutes. So let's go on. So an empirical formula, you actually you calculate the empirical formula whenever you are given the percent composition or the elements or the compound's elemental composition by mass. And so if we are, then we can determine the empirical formula. And the way that you determine the empirical formula, once again, guys, is you begin with the mass of each element. Okay? And if the percentages are given to you, then assume 100, and then just assume 100 grams of that sample is actually present. Then you find the number of moles of each element, and you divide each mass by its atomic mass. Okay? And then you divide all the numbers of moles by the smallest number of molecules. The resulting numbers are integers, they are the subscripts. That means if they are whole numbers or integers, then they are the actual subscripts of the formula. If the numbers, on the other hand, let me go back. So that means that if x happens to be an integer just such as this, 0.25, then the number will stay as it is. The same as is. If the integer happens to be greater than 0.75, then you're going to end up rounding up. Okay? And all this will make sense to you in a minute when you actually do apply it. So bear with me. If the number included is a decimal, it will be necessary for you to multiply to get rid of all of the fractions. Okay? For example, so if you have 0.25, if a number is between 0.25 and 0.75, then you're going to need to multiply it by 4. Okay? And if a number happens to be between 0.3 or 0.7, then you would need to multiply it by 3 to make it a whole number integer. And then if the number happens to be 0.5, then you would need to multiply by 2 to become a whole number integer. Okay? So again, let me clarify. If x happens to be less than 0.25, then the number will stay the same. If x happens to be greater than 0.75, then you just round up. Okay? And then if this does not work, if the number is not less than 0.25, or if the number is not greater than 0.75, but if the decimal value is between 0.3 or around 0.3 or around 0.7, then you multiply by 3. If the value of the decimal happens to be around 0.5, then you multiply by 2. If the value of the number is around or at 0.25 or 0.75, then you multiply by 4 to give you a whole number. Okay? So let's actually apply this. So this is where calculators can come in. And I have here a given substance has the percent composition of silver, which is 63.5%, nitrogen, which is 8.20%. So go ahead and underline those. And then oxygen, which is 28.2%. Okay? And I want to find out the actual formula that this percentage actually that it gives us. Okay, the actual formula of our compound. So first of all, we have here, I'm going to write down silver, nitrogen, just to make life easier, shape. You're given the percentage 63.5% for silver, 8.20% for nitrogen, and 28.2% for oxygen. Okay, so you're going to convert these percentages into grams. So you're simply just going to get rid of this percentage sign, and you're going to replace it with a gram sign. That's all you do. That's simple. Okay. Next, you're going to divide by the atomic mass of each element. So this is the atomic mass for silver right here. So you're going to get 63.5 divided by 107.9, and that'll give you 0.5885. Then you're going to get this number 8.20, and of course this 14.01 is the atomic mass of nitrogen. So 8.20 divided by 14.08, and you should get 0.5853. And then last but not least, you know that the atomic mass of oxygen is 16. So you're going to take 28.2, this grams that you have, and you're going to divide it by 16 to give you 1.763. Okay. Now we're going to take these numbers and we're going to see what we can do with it for, we're going to divide it by the smallest result. So you're looking at this number right here. Out of the three numbers that are given to you, which one is the smallest value? Well, the smallest value would be right here, would be nitrogen, right here. So you're going to take this number and you're going to divide all the other numbers by it. So you're going to take 0.5885 divided by 0.5853, and that should give you around 1.005. 0.5853 divided by itself 0.5853, and you should get 1. And then 1.763 divided by 0.583, and that should give you around 3.011. So going back, if you're looking at these numbers right here, and I'll use a different color pen. So you are looking at these numbers right here around the decimal. And we're going to go back using these numbers. We're going to go back and look at these values that I have. Is this decimal 0.005 less than 0.25? Yes, it is. Then the number will stay the same. So this number will stay the same. We won't do anything to it, so it's going to remain as 1. Okay? So, and then there is 0. There's nothing we can do, so this number will stay the same. It is 1 right here. And then we have 3.011. 3.011, again, this is less than 0.25. So you're looking at the decimal number here. 0.011 is less than 0.25, so the number stays the same, so we're going to have 3. Well, this right here, this is the result of your subscripts. This is what the subscripts are. So your silver has 1 atom of silver in it. Your nitrogen has 1 atom, and then your oxygen has 3. Of course, when you write it down, this is how it looks. But you know better. You know that this will actually form this is actually a chemical formula. It is an ionic bond. And you know that nitrate right here is a polyatomic. So instead, you're going to, you can write it with parentheses, which is fine. But since this is 1 atom of each, you don't have to, and you can just leave it as this, as an answer. So this is silver nitrate. So whenever you have 63.5% of silver, 8.20% of nitrogen, and 28.2% of oxygen, you will form silver nitrate. And this is the chemical formula that it produces. Okay. So go ahead and write here silver nitrate. That's what it makes. So moving on to our next page, let's go on to the next page right here and do example number 18. So if we do example number 18, right here, it says here, find the empirical formula for a substance that has percent composition of potassium, 56.6%, carbon, 8.68%, and oxygen, 34.7%. So we are trying to figure out, we have the percentages. So we actually went to like a mine or something, and we found this substance. We have no idea what the substance is, and we brought it back to our lab. And upon, when we brought it back to lab, upon further investigation, we found out that this substance has 56.6% potassium, 8.68% carbon, and oxygen is 34.7%. Well, this doesn't mean anything because we want to know what is that substance that's in there. So we need to find out the chemical formula. So you use empirical formula, you use this method to determine the empirical formula so you know what substance you have. Okay? So let's go back and let's do potassium right here. And remember, you start off with the percentage that's given to you. We're going to convert this percentage into grams simply by putting 56.6. Okay, that's it. And then we've got carbon also. Same thing. We're going to convert this into grams, so it's 8.68. And then we've got oxygen again. We're going to convert this into grams, which is 34.7 grams. Okay, no need to put grams over there because we're going to do so much more. The next step, remember, is, and you can look at this, but keep your eye, and we're just simply following this chart that you looked at over here. So the next step is we're going to divide by the atomic mass right here of each element. So you are going to be using your periodic table, but you're going to find the atomic mass, in this case for potassium, and when you look at your periodic table, it comes out 39.01. Okay? Your numbers might be a little different. I'm actually using a very different periodic table. Oh no, never mind. Mine's the same as yours. And then the next one is for carbon. The atomic mass is 12.01. And then for oxygen, we're just going to say 16. Because we just want that whole number. So go ahead and plug and play into your calculator. And the number you get when you divide these two numbers for potassium is 1.448. And then for carbon, you get 0.723. And for oxygen, you happen to get 2.169. Okay, so then what we do is that we take this number, so whichever one is the smallest ratio or the smallest number that you have. So you're going to take your smallest ratio and then you're going to divide the rest by that smallest ratio. So the smallest number that we have here is 0.723. So you're going to take this and you're going to divide everything else by that number. So this will be 0.723, 0.723, 0.723. Okay? So you're going to go ahead and you're going to divide by it. And when you do, you're going to divide by it. You get 2 right here. When you have 1.448 divided by 0.723, you get 2. Over here, you get 1, of course, because it's a number divided by itself. But over here, you get 2.169. And I'll put this one in my calculator and do it with you. So, okay, 2.169 divided by 0.723. And this is the number I get. So I get 3 for this. It's a whole number. So this is telling me the subscripts of my potassium, carbon, and oxygen. So now it's my job to actually figure out in what order I need to put this and what compound it produces. Usually, it may take you a little bit to figure out that what the substance is, but after some time you should be able to figure out that this is the formula of the substance, K2CO3, and the name of the substance is potassium carbonate. Okay? Potassium carbonate. So that's the name of the substance. The next one unknown salt. Analysis showed its composition to be sodium is 56.04 grams, carbon is 58.56 grams, hydrogen is 7.37 grams, and oxygen 78.02 grams. What is the empirical formula? Okay, so we found the substance, we have no idea what it is. Instead of giving us percentages, we have grams. Hey, that just does our job for us. That's not a big deal at all. That's great. So we've got sodium. So this is 56.04. And then we've got carbon. And I'm going to write 58.56. No reason to write grams at all because, we don't need them. So this is 7.37. And then oxygen is 78.02. Okay? So we've got this. Again, we're going to once again divide by the molar mass of each one. So use your periodic table. The molar mass of sodium is 22.9. The molar mass of carbon is 12.01. The molar mass of hydrogen is 1.01. And the molar mass of oxygen is 16. Okay? So now divide by this and you get 2.438. When you divide this mass, now for carbon, when you divide the two numbers for carbon, you get 4.876. And then dividing for hydrogen, 7.37 divided by 1.01 in our calculator should give us 7.297. And then I'll just do the oxygen, the last one with you, which is 78.02 divided by 16. That gives us a number, 4.87. And I just want to get up to 3 values. These numbers are exceptionally long, so 3 values, up to 3 decimal points or 4 decimal points is fine. I'll go ahead and get it up to 3 decimal points. That's fine with me. Okay? So sometimes these numbers are so long, so you want to have a stopping point somewhere. So past 3 decimal points, 3 places past the decimal is just fine. Okay? So now we find the smallest ratio that we got, and it is for sodium. So we're going to divide all the other numbers by the ratio for sodium, which is 2.438. And when I do, I get 1. 2.438 for carbon, 2.438 for hydrogen, 2.438 for oxygen. And when I put this in my calculator, for carbon, it should come out to be 2. For hydrogen, it should come out to be 3. And I'll go ahead and show you oxygen. So I'm going to take this number that I got, 4.876, and I'm going to divide it by 2.438. Okay? So, and I get 2. Okay. So, like I said before, it's going to take some time to actually be able to recognize what this compound is. But if you have 1 sodium atom, and then you have carbon, 2 carbons, 3 hydrogens, and again 2 carbons, and what substance is that? So that is sodium acetate. So you may want to have your polyatomic chart out in front of you if you feel like that would help you more with this and identifying it. Okay, then let's go on to the next one. It says a hydrate of ferric chloride has a mass of 10 grams. After heating, the mass is 6.0 grams. What is the formula of the hydrate? And for the empirical formula of a hydrate, you are just finding the amount of water. So that's all we're doing is that we know what the formula is. This is ferric chloride. Ferric chloride, that means that it is FeCl3. But we don't know what hydrate we have. We don't know what this mole or this number is for the hydrate. So that's what we're actually trying to figure out from this particular problem. So in this problem, they tell us that it is 6 grams right here. So I'm going to write 6 grams. And so they don't tell us the mass of the water that's present. But keep in mind that it is 100 minus 6. So here you can actually put not 100, 10 minus 6. So they give us 10 grams of it. So 10 minus 6 will actually give you 4 grams of water, which is what we have here. Okay? So this is actually our H2O that we are actually trying to figure out. just for each of the substance. Now we're going to divide by the atomic number. Okay, this is the atomic mass. Atomic mass, or the molar mass of the substance. And of course, this is the, I'm going to write MM for molar mass. Okay, this is molar mass. So that would be 18.02. So I'm going to take that mass and I'm going to divide it, 6 divided by 162.2. So it's actually in capital, it will be 6 divided by, and it should give you a number 0.003699. Okay. In this case, I took more than 3 decimal places only because there's a 0, so I decided to take a little bit more, and that's fine. And then in this case, and I'll do the last one with you. So it's actually oxygen, which is 4 divided by 18.02, because I'm taking this mass here divided by this. And that's the number that I have. It is 0.22198 that I get. Okay? Now keep in mind that I'm going to divide by the smallest ratio, and the smallest ratio is right here, 0.03699. And when I do, I get 1 as my answer. I'm going to take this and I'm going to divide it by my smallest ratio again. And my smallest ratio is 0.03699, and that should give me a 6. So in this case, I now know what X is for water. And in this case, it is ferric chloride hexahydrate. So this is the name of the compound that I have. Okay. So the 6 is actually goes right here. Okay, that's where the 6 goes. And notice that this one is actually the moles for ferric chloride. All right. So now let's go ahead and do our next problem. And there's several different types of empirical formulas, so you really need to be careful and know what each problem is asking and how to be able to do the different problems that are being asked here. Okay? So a hydrate of magnesium sulfate has a mass of 13.52 grams. This sample is heated until no water remains. The magnesium sulfate in hydrate has a mass of 6.0 grams. Find the formula and the name of the hydrate. So we've got here we're given a mass, total mass, and then we're given the mass of one of the actual compound, which is 6.60 grams. That's just the mass. So we can actually find out how much water. This is the anhydride. So that means there's no water mixed in here, and clearly when it was heated, it was heated until no more water remained. So how much water was present at the very beginning? So we can figure that out. We can just simply subtract 15.52 minus 6.60, and you get 6.92 grams of water. And this is the water that, remember, was heated or it was evaporated. So don't be mistaken, but it is 6.92 grams. Okay, so now we're going to find out. Remember that on the side you need to find the molar mass. So we're going to find the molar mass of magnesium sulfate. And go ahead and do that. And when you do, you find out that magnesium sulfate is 120.38 grams per mole. So that's how much we have. For water, H2O, you should know this, but the mass is 18.02 grams per mole also. So let's start off with magnesium sulfate, H2O. So we have magnesium sulfate, and in this case, the magnesium sulfate that we have, the mass is 6.60. So we're going to start off with the mass of it. No need to write grams, right? Because we're going to do so much more to find out the formula. So, and we also know the mass of the water, which is 6.92 grams. We're going to divide by the molar mass of each substance. So divided by 120.38. and divide it by 18.02. And when we do, you get for magnesium sulfate, when you divide 6.60 divided by 120.38, you get 0.0548. And for the water, 6.92 divided by 18.02, you get 0.03840. And then, of course, you find the smallest ratio. The smallest ratio in this case is 0.03840. And you are going to divide, let me check. Did I make a mistake on here? Hold on, 6.92 divided by 18.02. I did it. Okay. So let me go ahead and fix my mistake. I'll be right back. Okay, so I fixed it, and it turns out that it is actually, and I did it in the calculator, it is 0.3840. Okay, so we're going to divide by the smallest ratio. In this case, that is of the magnesium sulfate. So 0.0548 divided by 0.0548. You do. You get 1 right here. And I'll do the last one with you. I'm going to take 0.3840. And I'm going to divide it by the smallest ratio, which is 0.0548. And I do get this really long number, right? So this is the number that I get for. I'm going to keep this number as it is. Okay? So I'm going to put this number down at 7.007. I'm going to forget about it. Okay? But notice that this number actually goes into the values that I was talking about before. So this is the values that I was talking about before. Again, this ratio, this decimal number, 0.007, is less than 0.25. So if it is less than 0.25, then the number stays the same. So my decimal is less than 0.25, so my number will actually remain the same, and it is 7. So we're going to keep that 7. So this is magnesium sulfate, and this is 1 mole of magnesium sulfate. So I don't really need to write this 1 right here. Okay? And then I have heptahydrate. Okay? So I'm going to write the name down. Magnesium sulfate. Heptahydrate. There we go. So that's my answer right there. Okay. So, okay. So sometimes, when dividing by the smallest result, a decimal is produced, and you must multiply by the appropriate values to have a whole number subscript. So the whole reason why I was actually even talking about this right here is because we want to have a whole number subscript. So go back to your notes and write down right here what you want. This is for do this to have a whole number subscript. Okay, that's when we look at that. All of this right here, these rules in here. Okay, so let's go back to our problem. So the decimal values are generally take the form of 0.25, 0.33, 0.5, 0.67, and 0.07. And each one of these, you multiply it by its prospective number to give you that whole number. For example, 0.75, well, you can multiply this 0.75, you can multiply by 4 to give you a whole number, the next whole number. Okay? Just like 0.5, you can multiply it by 2 to give you the next whole number. So let's look at this. We have sodium, sulfur, and oxygen. We went digging and we found a substance, a rock, I guess, and a clump of substance, of clay, I guess, and when we brought it back to lab, we found out that 29.09 grams of it was sodium, 40.56 grams of it was sulfur, and 30.35 grams of it was oxygen. I can also say 30.35% of it is oxygen, 40.56%, or 29.09% is sodium. So I could use those numbers as percentage, because remember, percentage and grams are one and the same. It's just replacing the percent by grams. So now we're going to divide by the molar mass of each of the substance. So I'm going to divide, I know it's 29.99 on your periodic table, but I'm going to go ahead and round it up this time and just say it's 23. The sulfur, on the other hand, we're going to say it's about 32.07, and oxygen is about 16. So we're going to go ahead and take this 29.09 divided by 23 to give me 1.265, 40.56 divided by 32.07 to give me 1.265, and then 30.35 divided by 16 to give me 1.897. Okay. So now that I have a number, I am going to be looking at the smallest ratio. In this case, the smallest ratio was a tie between two numbers that are the exact same, 1.265. That's okay, because we can use that number. So we're going to take this number divided by itself to give us 1, take this number divided by itself to give us 1, and then we're going to take 1.897 divided by 1.265 to give us 1.5. Now, this is not a whole number, and it's too big of a rounding for you to just round it off to the next whole number. So it is too big for you to do that. So instead of rounding it off, we're going to actually now, we're going to go ahead and take this number, and we're going to multiply it by 2 to give us the next whole number. And when we do, because remember, in our notes, we say if the number is 0.5, then you multiply it by 2. Well, this number definitely is. This number right here, that's definitely 0.5. So we're going to multiply it by 2, and when we do, we get 3. What we do on one side, you must do the same to the other element. So you're going to take each one of these, this 1, and you're going to multiply it by 2 to eventually get 2, 2, and then the oxygen is going to be 3. Okay. So when you put this together, your formula is sodium disulfate. Okay. So we want to write that down also. That is the chemical formula that you're going to have when you start writing down sodium, sulfur, and oxygen. So we're going to write down sodium disulfate. Okay, so we have sodium thiosulfate right here. All right then, let's move on to the very last one. So flip your page over. We have one more empirical formula problem to do, and so it's right here. An ionic compound has a percent composition of lead is 76.59%, phosphorus is 7.63%, and oxygen is 15.77%. Find the empirical formula. Okay, so we're going to go ahead and put everything in here. Lead is Pb, and so lead is about 76.59. We're going to convert that to grams. No reason to write grams right here. Then we've got, we've got oxygen, which is 15.77, and then I'm going to just write phosphorus right here. Phosphorus is 7.63. Okay, grams. We're going to divide by the molar mass of each of the elements. Lead is 207.20, oxygen is 16, and phosphorus is 30.97. Okay, and then when we do divide this, we get a ratio for lead to be 0.3696. Oxygen happens to be 0.9856, and phosphorus happens to be 0.2464. Divide by the smallest ratio. So the smallest ratio here is from phosphorus that we get. So we're going to divide everything by 0.2464. So go ahead and do that. Divide everything by that. I'm going to go ahead and write it. And when you do, you happen to get, for lead, you happen to get 1.5. For oxygen, you happen to get 4. And for phosphorus, you happen to get 1. But this is 1.5. So going back to what I talked about earlier, where we want this to be a whole ratio, you're going to multiply this by 2. And when you do, you get 3. What you do to one, you must do to the others. So you're going to multiply everything else by 2 also. And this is going to give you 8 times 2 will give you 2. So looking at this equation, this is what comes out. So you've got Pb 3, oxygen is 8, and phosphorus is 2. Usually what happens is that the percentage that we give you, that's the order of the elements. So in this case, it's going to be Pb3, phosphorus is 2, oxygen's 8. But you've got to be able to recognize where the polyatomic ions are. There is no such compound that you know of so far that exists like this. But if we reduce the 2 out of this, this quickly becomes then lead with a 3, and then this becomes your phosphate. Okay, so this actually becomes lead 2 phosphate. So have your polyatomic chart in front of you so that you can first remember how to write these out. Okay, so if you quickly reduce this by 2, it becomes phosphate. Okay, the very last example of empirical formula is given 50 grams of an unknown compound. Analysis showed its composition to be carbon is 40.86 grams, hydrogen's 9.143 grams, and so determine its empirical formula. So again, you're going to divide each one. I'm going to get rid of the grams, and I'm going to divide it by its molar mass. Okay, and when I do, I get 3.402, and over here I get 9.052. I'm going to divide by the smallest ratio. In this case, it's 3.402. So I'm going to divide on each side by the same ratio. And over here I get 1, but over here I get 2.66. Now the point of this is, look at this ratio right here. This is 0.66. So if we go back to what we had originally talked about in your notes, so right here, we can multiply, it is 0.66. So we can actually multiply by 3 to give us a whole number ratio. So if we multiply by 3, this will give us 7.98. Now this 0.98 is, remember, that it is greater than 0.75, so we round up. So this will actually round up to about 8. And what we do on one side, we must do on the other side. So we're going to multiply this side by 3, and it's going to give us 3. So in this case, we have carbon 3H8, which is, of course, the formula for propane. Okay. So this is my lecture on empirical formula, and follow this lecture, the next lecture that you need to listen to is molecular formula to get an idea of how to combine both empirical and molecular formula. Okay, thank you. See you guys soon. Bye.